All right, in this video we're going to go over the AP Calculus AB 2018 exam for response question number 1. So we're given this information about an escalator and we're given a rate in. Here's our rate in, R of t, enter a line modeled by R of t, and then we exit the line. Exit the line at a constant rate of that. So this is sort of a classic free response question type where we're given a rate in, a rate out, a rate of addition, a rate of subtraction. And so often in these questions, like here in part A, we're just asked about how many people come in. And when we have this type of situation, it's just the definite integral on the interval that they're asking about. So in this case, from 0 to 300 of that rate in expression, because the definite integral, by definition, gives you the net change of whatever rate of change you're integrating. So when we're integrating R of t, which is the rate of change at which people get in line, then the definite integral on some interval is going to give us how many people have gotten in line during that time period. Question number 1 is a calculator allowed question, so you're just going to want to plug that into your calculator. When you do that, you get 270. Part B says during the time from 0 to 300, there are always people in line for the escalator. How many people are in line at time t equals 300? When you first read this, the first sentence there of there are always people in line seems a little strange, maybe even not necessary, but we'll talk about why I do think that is necessary in just a minute. But again, this is sort of following the classic, if we ignore that first question for a moment, this is sort of following, or first sentence, excuse me, if we ignore that first sentence for a moment, we're following the sort of classic example. You've got a rate in and a rate out. First question, how many people come in? Second question, how many people do we have? So in doing that, there's 3 things we have to consider for the how many people do we have now piece. So for part B, there's 3 parts to my answer. There's 20, which is given to me as the number of people in line when we start. 20 people in line, so I need that. Then plus the number of people who get in line, which is the 0 to 300 of R of t, which we just did. And then minus the number of people who get out of line. Now there's a couple ways you could write this down, this number of ways, or number of people who get out of line. But what I'm going to do is I'm just going to think about this in sort of the most, I think, straightforward way possible, which is we're losing 0.7 people per second for 300 seconds. So I'm just going to multiply 0.7, the rate at which people get out of line, times 300, the length of time for which people have been getting out of line. You could, if you wanted to, take this same expression, and let's just rewrite it a little bit here. It's going to be 20 times the integral from 0 to 300 of R of t minus 0.7 dt. Where now what I've done is I've taken my integral and made it the overall rate of change, because it's the rate in and the rate out being subtracted, and I can put that all into the integral. And that's of course the same, because when you have addition or subtraction inside the integral, you can split it up into 2 separate integrals, so you can do 2 separate pieces like we did here. And also the definite integral of a constant is just that constant, 0.7, times the variable. So what we would do is you would get the antiderivative here would be 0.7t, plug in 300, plug in 0 and subtract those things. And so you're going to get 0.7 times 300 minus 0. So it will be the same thing. When you calculate that all out, again, this is calculator allowed, you're going to get 80 for the answer for part B. So just to come back to that first sentence a little bit here, I said that it was weird to me when I first read that there are always people in line for the escalator. Why do I care? I don't really actually care. If I didn't really think about it, I would have done the same thing, or if I was just like, I don't know why they told me that, but I'm going to ignore it and just do what I think I should do, I'd be okay in this case. The reason that it is actually important, though, is that this rate out, 0.7 people per second, only makes sense if there are some people in line. And you could work out the math and figure out that there are always some people in line as you do the problem, but starting with 20, adding this many per second, subtracting this many per second, you can figure out that there are always people in line. But they're just telling you that so that you know that this 0.7 applies the entire time. Okay. Part C, what is the first time that there are no people in line? Well, we know, and it's important to notice also, that up until here we're talking about from 0 to 300, but now in part C we start talking about greater than 300, because again we know there are always people in line up until 300. So now after that, what's the first time that there are actually no people in line? Well, we know that at time t equals 300, there are 80 people. And from then on, we add no one, because we're given a rate of change of 0 for t greater than 300. And then we're still losing 0.7 per second. So if we just think about that, okay, I've got 80 people at time t equals 300, and I lose 0.7 per second. How long is it going to take me to go from 80 to 0? Well, that's a simple enough equation. Just do 80 minus 0.7t equals 0. Solve that for t, and you're going to get approximately 114.286. Now that's not the answer. That 114.286 says that we started with 80 people, but we started with 80 people when t was 300. So 300 seconds have already gone by. So this 114 represents the number of seconds since it was 300 seconds. So in total, our actual answer is 414.286, because we're adding that 300 to the 114.286. Part D, I'm going to go ahead and just clean all this stuff up, because I don't really need any of this, and I just would like some more room here. So if you haven't copied all that down yet, of course there's a video, so go ahead and pause it. I'm going to get rid of stuff. Go away. Go away. Okay. So for part D, we're looking for a minimum. And anytime we're looking for a minimum or a maximum, the first thing we want to think about is critical numbers. And critical numbers are when our derivative is 0 or undefined. So our overall derivative here, our overall rate of change, is r of t minus 0.7. I want to figure out where that equals 0 or is undefined. If I look at the equation for r of t, though, that's just a polynomial that's never going to be undefined. So we're just looking for when this is actually equal to 0. Again, this is calculator allowed, so you're going to solve that on your calculator. When you do that, you should get two answers. T is about 33.013, and T is about 166.575, if I did my math correctly. So we could have a minimum here, but we could also have a minimum at 0 or 300, because on a closed interval, which we're given a closed interval here, the maximum or minimum could be the starting point, or it could be the ending point, as well as the critical numbers. And so I always like to think about the graph of this derivative before I worry about which one is my maximum or my minimum, especially for a calculator aloud question like this, where I like to use the graph to solve the equation. And if I do that, and I just draw a rough sketch here, very rough, of course, you're going to get something for this derivative that looks something like this. Not quite as squiggly, but something roughly like that. And so on that derivative graph here, we know that this one and this one, those are my two zeros here. There. There. Well, this second one here cannot be my minimum. No. Because the derivative is changing from a positive value, positive derivative, to a negative derivative. That means we have a local maximum here. So that one I don't actually even care about at all. But similarly, this first endpoint, t equals 0, that can't be the minimum either, because the derivative is decreasing, or excuse me, the derivative is negative, meaning the function is decreasing from 0 to 33. So whatever the value at 33 is, it has to be less than the value at 0. So I actually don't care about either of those things. So I'm going to say no to you too. So I just need to know how many people are in line at 33.03, and then how many people are in line at 300. I need to know those two values, and whichever one is the smallest is the minimum. So I'm really just going to follow the same process that we did in part B, and just figure out how many people are in line at each of these different times. So as I said, we're just going to do the same thing that we did in part B. And in part B, we already know that it's 80 people at time t equals 300. And the process that we did in part B was we started with 20. Then we added the definite integral from 0 to wherever I wanted to figure it out, 33.013 of r of t, then minus 0.7 times that same time value. So again, 33.013, because we've been losing 0.7 people per second for all of those 33.013 seconds. If I do that, I'm going to get 3.803. And so that's the minimum. So the question asks at what time is the minimum, and so that's 33.013. And then to the nearest whole number, how many people, and so that's going to be 4, because we're rounding our 3.803 to the nearest whole number like it suggested. So I feel like if you think about the graph here a little bit, you can save yourself some time. I don't care what that value is. It's not hard to find, but I just don't care. Same here. When you check your answers with the College Board scoring guide, what they'll always do is they'll just make a table, and they'll just say, okay, what are my candidates? T and people. And they'll say, okay, we need to think about 0, 33.013, 166.575, and then 300. And then they'll just list the values. So this one was 20, we know. This one we just figured out is 3.803. You can find this one the same way. It actually ends up being 158.07. And then 300 we know is 80. So the College Board always just figures out what's the output value at all of the candidates and says, okay, well, this one is the lowest. I feel like you can easily eliminate a few by just looking at the graph. Save a little bit of time. Okay, so that's question 1 from 2018.